Hello everyone, welcome back to Diksha Karnataka YouTube channel, and in the midterm series today I am going to discuss another important chapter, that is moving charges and magnetism. It's a very important chapter. So here we will start as usual with the quick theory revision of the entire chapter. Also, if you are watching our channel for the first time, or if you are watching our videos but not subscribing to our channel, I request you to please subscribe to our channel and obviously join the WhatsApp channel. The link of the WhatsApp channel is given in the description of this video. Here you will get all the class notes, PDFs, etc. So don't wait, join the WhatsApp channel and also subscribe to our channel. Share this video with your friends so that they can also study along with you. Now without much delay, I want to start today's lecture. So first let us look into the most important concept from this chapter: Lorentz force, force on a current carrying conductor, motion of a charge in a magnetic field, Biot-Savart's law, Ampere's law, solenoid and galvanometer and their conversions. Okay, so these are the main topics from this chapter. So we will discuss everything in this short video, and I will try to keep it less than 30 minutes, as much small as possible. Now let's start with Lorentz force. So what is Lorentz force? Lorentz force is basically, we have learned that in our electrostatics chapter, that if we keep an electron or any charged particle in an external electric field, it experiences a force, right? So if we keep a charged particle, normal charged particle in an electric field, okay, charged particle Q, it experiences a force. What is that force? Force was given by Q into E. Right, so this is electrostatic force. This force is called electrostatic force. Right, now what will happen to this charge if I keep this charge into a magnetic field? So will it experience as a force? Now that depends on one thing, that whether the charge is static or it is moving. If it is moving, then based on the relative direction of the force, relative direction between the magnetic field and the velocity, there will be two possibilities. Okay, either force will act or the force will not act. Now if the charge is static, no force will act. If the charge is static, then no magnetic force will act on a charged particle. Just remember this. This is a very important point to remember. I am telling it a little bit in a hurried fashion, but this is very important point to remember, that static charge do not experience magnetic force. Now what is Lorentz force? Lorentz force is basically, if you consider electric field as well as some magnetic field. Now magnetic field is denoted by the symbol B. Okay, B represents magnetic field, E represents electric field. So if you keep both electric field and magnetic field present, and if you have some moving charge, in both the presence of both fields, then whatever is the total net force experienced by this charge is called the Lorentz force. So both electric field and magnetic field are present, and if the charge is moving in that presence of electric and magnetic field, then the net force experienced by this charge is called Lorentz force. So when a charge moves through a space having both magnetic and electric field, it experiences a force. Now force due to electric field is given by the simple formula Q into E. Now because we are talking about vector form, so that's why we have taken this into a vector form. So Q into E, and force due to magnetic field, this is a new term that we are learning in this chapter, that is Q into V cross B. Okay, V is velocity vector, V is the velocity of the charge. Okay, it not only have the magnitude, it also has the direction. So V cross B gives me the magnetic force. So the total force on the charge can be written as Q into E plus V cross B. So this is the total net Lorentz force. Now there are special case, obviously special case is if electric field is 0, then the force is only magnetic force, and that force is also called Lorentz force. Okay, Lorentz force in general, the general Lorentz force is both electric and magnetic field are present. Okay, now the special case, because this chapter related to magnetism only, we will not discuss too much about electric force in this chapter. Okay, but we will mainly focus on this magnetic force part, which is actually the magnetic force part of Lorentz force itself. Okay, combining these two forces is totally called Lorentz force. Individually, this is electric force, this is magnetic force, but in this chapter we will only focus on magnetic force specifically. But you have to remember that Lorentz force is a combination of electric and magnetic force both. Okay, and as you can see, there is a cross product. Cross product means if you only consider the scalar part, then the scalar part is given by q v_b sin theta, right? Magnitude is q v_b sin theta. So if the angle between the velocity vector and magnetic vector is theta, if the angle between magnetic vector and velocity vector is theta, then this will be q v_b sin theta. If theta is 0, then this force becomes 0. If theta is not 0, then this force is obviously not 0. As simple as that. For theta equals to 90 degree, the force becomes maximum. Now let's move on to the few points. Force on a negative charge is opposite to that on the positive charge. So the formula that we have learned is valid for both positive and negative charge. Now if you put negative charge, then the direction will be opposite to that of the positive charge, obviously, right? The vector product makes force due to the magnetic field vanish or become 0 if velocity and magnetic field are parallel or anti-parallel. So if velocity and magnetic field they are parallel means velocity and magnetic field they are parallel means theta equals to 0, and if velocity and magnetic field they are anti-parallel means angle is 180 degree. Sine 180 degree is also 0. So both cases the magnetic component of the force will become 0. Okay, so even if the charge is moving, if it is moving parallel to or anti-parallel to the magnetic field, then there will be no Lorentz force, no magnetic component of Lorentz force. The magnetic force is 0 if charge is not moving, that is velocity is 0. Only a moving charge feels the magnetic force. Now these points are very important for your MCQ that you are going to come in your midterm and your board exam as well. So this is a very important points to remember. Now let's move on to the next part. Force on a current carrying conductor. Now we are talking about force, we were talking about individual charges, right? Now if you consider a current carrying conductor, simple conductor carrying current kept in a magnetic field, then what will happen? The charge that is present inside the conductor, that charge will also experience a force, obviously Lorentz force, and you can calculate it, and the total force that can be calculated will be given by BIL sin theta, BIL sin theta, BIL sin theta. Okay, so this is the expression for force. In vector form it is given by I into L cross B. Now remember that current I is not a vector quantity. Okay, so there is a quiz question for you in quiz, especially science quizzes. There was a question that a quantity which has a direction but not a vector quantity is, name one example. The example is current. Okay, the reason is little complicated. Actually, even though we consider the direction is not very common, so that's why there are some reasons behind that. You can go and study from Wikipedia or Google it. Nowadays a lot of AIs are there, so you can study from there as well. Now but length is a vector quantity, magnetic field is a vector quantity. So L cross B is the vector form, whereas BIL sin theta is the scalar form. Okay, now let's move on. Just formula you have to remember, nothing else. Based on this formula, small numerical questions and one more theory derivations that we will do in our 2, 3, 5 marker derivation. That derivation requires this formula to be used. Now, motion of a charge in a magnetic field. Now let us consider only, as I said, in this is a chapter about magnetism, so we will only discuss about motion of charge in magnetic field only. So a charge moving in a uniform magnetic field will experience a force. Charge moving in an uniform magnetic field will definitely experience a force. This force acts as centripetal force and produces a circular motion perpendicular to the magnetic field. Now if theta is 90 degrees, so if the theta QVB sin theta we have learned, so if the magnetic field and the velocity vector, if they are perpendicular, that is theta equals to 90 degrees, then the magnetic component of the Lorentz force will act as a centripetal force. What is the meaning of centripetal force? We will see that in a while. The centripetal force means when the object is moving in a circle, it experiences a force, right? So that force will make it rotate in a circular path. Okay, so you see that this, when the magnetic field cross means into the paper. Now cross and dot, who don't know it, cross means what? So if you see a cross on a wall, okay, this is like a target, right? You want to hit that cross, you want to hit it here. So that means basically it is going into the paper. Okay, so going into the page is cross, dot means coming out of the paper. This is out of the paper. Now this is a trick that we use. This is into the paper, because we are using a 2-dimensional medium to show 3-dimensional things. Okay, we use these tricks. These are very, very common tricks. Cross means into the paper, dot means out of the paper. Okay, so here as you can see, the magnetic field is into the paper, okay, and velocity is always perpendicular to the direction of magnetic field. Okay, so magnetic field is into the paper, velocity is perpendicular. So what happens to the charge? The charge will rotate in a circular motion. Okay, and we have to find the radius of this motion, we have to find the angular frequency, etc. There are the derivations are sometimes important. 2, 3 marker questions might come from that as well. We will see that in a while. But what will happen if the angle theta is not 90 degrees? Okay, if it is between 0 and 90, if it is between 0 and 90, then there will be a component which will be parallel to the magnetic field. Okay, this is a 3-dimensional picture. There will be a component parallel to the magnetic field, and this motion will not be a perfect circular motion. It will be like a spring. The motion will resemble a spring. If you have seen a spring, okay, that stays inside the pen, okay, or the slinky that you play, the plastic slinky, okay, that you can buy it from some shops, gift shop, and used to play, right? So the shape is like that. This is called a helix, and the motion is called helical motion. If a velocity component is along B, so that means there is a component along B, the angle theta is not 90 degree, it is between 0 and 90 degree, theta in between 0 and 90. So in that case, velocity will have a component along B. This component remains unchanged, as this motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to B is as before a circular one, thereby producing a helical motion. Okay, so this will produce a helical motion. Now here we are doing the small derivation. So radius of the circular path. So first of all, obviously you have to remember that for any circular motion, centripetal force is must, and centripetal force has to be provided by some other force. Centripetal force is not like a gravitational force or like a electrostatic force. Okay, it is a required must have force for circular motion, and some third party force will provide this required force. So centripetal force is a required force. Okay, gravitational force is a universal force. Okay, it will always present. Gravitational force is always present. Okay, in case of gravitational circular motion, for example, moon is rotating around earth, right, in a circular path. So moon, and the gravitational force between moon and earth is actually providing the required centripetal force. The gravitational force between earth and sun is providing the required centripetal force for earth to maintain its rotational motion around the sun. So that is something. So some force has to provide the required centripetal force. So student sometimes gets confused about it. That's why I always stress on this factor. So centripetal force is given by mv square by r. Now that force has to be provided by something. Who can provide this force? In this case, only force that can provide is the magnetic force, right? The magnetostatic force, or not static force, magnetic force acting on the moving charge. So that is qvv sine theta. Now theta is 90 degree in this case, so sine theta is sine 90 is 1. So we can write mv square by r equals to qvb. And from there, if you compare, you can calculate the radius of this circular path. Now if velocity is high, radius is high. If magnetic field is high, radius is small. Okay, remember this relations. Okay, based on this you might face some MCQ questions. Angular frequency can be calculated. Omega is equal to qb by m. Time taken for one revolution is called the time period. That can be calculated by 2 pi by omega. You can put that value over here and you will get 2 pi m by qb. Okay, so this is the expression for time period, right? So these are the basic formulas that you have to remember and understand. This derivation sometimes comes. Okay, easy derivation, one line derivation, not much, right? Now let's move on to Biot-Savart's law. Now Biot-Savart's law is the most important law, very highly possible chance of coming it as a 3-marker question. So whenever you are answering this, you have to draw a diagram like this. The diagram represents a current carrying wire, okay, having current I, and you are trying to find a magnetic field at some arbitrary point P. Okay, the point P is not important, but what you have to do is that whenever you draw the point P, from there you have to take a small element dl. It is called a current element. Okay, dl, and join the center of this dl to point P. Okay, so that it appears to be perpendicular. Then you take the direction of the current at dl, and then you draw the angle theta. So these are the very important parts that you have to do. This distance is given by r. Now it comes to Biot-Savart's law. The statement says that the magnetic field at P, due to this small current element dl is given by dp proportional to the current I. The dbp is proportional to the length of the element dl. It is inversely proportional to square of the distance, and it is directly proportional to sine of the angle theta. And if you combine all of them together, you will get this as mu naught by 4 pi I dl sine theta by r square. So mu naught by 4 pi is the constant. Mu naught is called the permeability of free space, right? And the constant mu naught by 4 pi has a fixed value, like you remember 1 by 4 pi epsilon naught. Similar to that, mu naught by 4 pi has a fixed value, which is 10 to the power, approximately 10 to the power of -7 Tesla meter per ampere. Now Tesla is the unit of magnetic field. So if I missed that, I am covering it now. Tesla is the unit of magnetic field. Okay, so these are the very basic formula, and you have to remember this statement. There are a lot of times it comes not only in midterm, but it will also come in your board exam as well. Okay, mu naught is called permeability of free space. Now let's move on. Now magnetic field versus electric field, there is a comparison which is very essential for us to know. Okay, so both magnetic field and electric field are long range and depends inversely on the square of the distance. Okay, so if you are moving away from the source, okay, then the magnetic field as well as electric field both varies inverse square principle. Okay, the principle of superposition applies to both fields. The electrostatic fields are produced by a scalar source, namely a static charge. Okay, static charge is a scalar quantity. So electric field, which is a vector quantity, but it is produced by a scalar quantity. Very interesting, right? The magnetic field is produced by a vector source. Okay, current element. Generally we consider current element as the source of magnetic field. Okay, so like static charge produces electric field, a current element produces magnetic field, and it is a vector source because length dl is basically a vector quantity. Okay, so very important point to remember. The electrostatic fields is along the displacement vector joining the source and the field point. The magnetic field is perpendicular to the plane containing the displacement vector and the current element ideal. Okay, so electrostatic field along the displacement vector joining the source and the field point. So you can this is the source, you can join it electric field like this will give you the direction of electric field. Okay, where either this way or opposite way based on the charge. Okay, but to find the magnetic field you have to take the cross product ideal sine theta. So there is a sine theta involved. Sine theta involved means it is a cross product, so it will be perpendicular to both. Okay, vector and the current element. Okay, so both way it is perpendicular. There is a angle dependence in the Biot-Savart's law which is not present in the electrostatic case. So ideal sine theta, so as I said, because it's a cross product. Okay, sine theta, if you see in an expression of vector quantity, if there is a sine theta involved, that means it represents a cross product. Okay, if it is a scalar quantity and if you see a cos theta, that means it is basically a dot product of two vectors. That is how you can understand. Once you solve more and more questions, you will have this idea slowly. Okay, maybe not in class 12th, but later on in future you will have that idea. Okay, now magnetic field due to a straight conductor. So magnetic field due to a straight conductor, this is sufficient for your board exam. There is a little complicated formula also for those who are preparing for KCET or Comet K or JEE, but this formula I will not go to that formula. This is the basic formula due to a magnetic field due to a straight current carrying wire, and it is given by mu naught I by 2 pi r. Mu naught I by 2 pi r is the expression for magnetic field due to a straight, very long, infinite long current carrying wire. Okay, now current carrying circular loop, this is the very important concept, and the derivation I will cover it in 235 marker section, and the derivation is coming year after year, almost every year. This derivation is again very important. So here we have a current carrying loop which is basically excuse me, producing a magnetic field at this point P. You have to find the magnetic field at this point, and it is given by mu naught I r square divided by 2x square plus r square to the power 3 by 2. So this is also very important formula to remember. Now at the center this can be simplified. This formula, based on this formula you might face small numerical questions. So this formula you have to remember. Right, now this is a special case from where you can show that. So there is a question, it came only once I think in the past that show that the current carrying wire is basically behaves as a magnetic dipole. Okay, so that means you have after deriving this, you have to put this approximation, that is x is very very greater than r. So that means this point, this is x by the way, if you are wondering, and this distance is r. Okay, so if you take the point P very far away from the current carrying coil, then it basically gives you the expression for like a dipole, electric dipole. This expression is very much similar to that of electric dipole, only the constant there was 1 by 4 pi epsilon naught, here it is mu naught by 4 pi. Obviously that was for electric field, this is for magnetic field, so that is the basic difference. There it was 2p by r cube, here it is 2m by x cube. Okay, so this represents a dipole, and that is a proof of a current carrying loop can behave as a magnetic dipole. Now this derivation is not super important, just for perspective I gave this theory to you. Okay, just to understand that a current carrying loop can be considered to be a magnetic dipole. Now Ampere's circuital law statement is important. The magnetic field around a closed loop depends only on the electric current passing through the loop, and it is given by B dot dl equals to mu naught I. Okay, the statement is important. Now solenoid, so if you have seen solenoid is basically a cylinder having lots of turns. Okay, so it looks like this, right? And here these are the magnetic field lines, so you may be confused, that's why this is solenoid, and the magnetic field lines are drawn like this. So solenoid is basically something which produces a magnetic field, and the center of the solenoid, at this inside this cylinder, okay, a fixed constant magnetic field is produced, and that value of the constant magnetic field is given by mu naught n I. Okay, mu naught is the permeability. Obviously, what is n? N is number of turns per unit length. Very important. This is number of turns per unit length. Per unit length means so it does not depend on the total number of turns. Total number of turns can be very high. Okay, but if you consider unit length means 1 meter length. Okay, if you consider 1 meter length, okay, then whatever is the total number of turns in that length, that will give you the magnetic field. Okay, now what if the solenoid is small and the total length is not even 1 meter? Okay, then what you have to do? So the best way to do it is that suppose you have 100 turns and the length is say 1 centimeter only, or say 10 centimeter. Then how can you calculate the number of turns? To calculate that, easiest way is to take the total number of turns, divide by the length. Now length you have to convert it into meters, that is the major thing. Okay, length you have to convert it into meters. Okay, so you can cancel 1 0 and you will see this will be 1000 total number of turns. Okay, so total number of turns you can calculate in this way. Clear? If you have any doubts, any questions, please mention in the comment section below. Also, if you have not yet subscribed, please don't forget to subscribe to our channel. The growth is very very important for us. Share this video with your friends so that our channel can grow very quickly. Now next is force between two parallel currents. This is also another important derivation and we will cover it, so don't forget to watch my 235 marker video, which will come today only. After the next video, which will be MCQ, obviously after MCQ 235 marker section we will do the derivation. So here we have two parallel wire, okay, they are carrying current. Okay, so either you consider these two wire or you consider the next two wire. Okay, why so? Because if you see that the first case, if you consider these two wire, okay, both cases current is being passed in the same direction. Okay, these are called parallel currents. These are parallel currents. Okay, so and if you see these two wire, okay, one is taking current in this direction, another one is taking the current in the opposite direction, so they are called anti-parallel currents. Okay, so they are parallel and these are anti-parallel, right? So first of all, the force between these two current carrying wire, this wire will produce a magnetic field, this wire will also produce a magnetic field, and they will interact between them, and because of that there will be a mutual force between these two wires. The expression for the force is given by mu naught n Ia Ib by d into L. Okay, so this is the total force. Now generally these two wires are very long, so if you take a small portion of this wire of length L, then this is the force due to that portion only. Okay, now the force between 1 and 2 and 2 and 1 will be same but opposite. So if this force on this say suppose the force on the one charge is F12, so if this is F12, okay, then this will be F21. Okay, and d is the distance between the wire, d is the distance between the wire. Length, you have taken certain length. Okay, so if you divide this force with this L, then you will get the force per unit length. Okay, force per unit length, which is basically a constant value. Constant value means it only depends on the current and the distance. Okay, so the now there is a important part from this derivation is that define ampere. Okay, define ampere from this. So the ampere is the force when two very long straight parallel conductors, each of the negligible cross section and placed 1 meter apart. So if you keep this distance d equals to 1 meter, okay, then would produce on each of these conductors a force equal to 2 into 10 to the power of minus 7 newtons per meter of the length. So what is the meaning of that? If you put everything 1, so current I equals to 1, this I equals to 1, okay, length equals to 1. Now n is number of turns, but number of turns is not important here, over here, so only 2 wires are there, so not super important. So if you add everything, you will see that if this is 1, this is 1, this length is 1, this distance is also 1, then what will happen? You will have force equals to only mu naught. I think there is a mistake, there will be a 2 pi over here. Yes, there will be a 2 pi over here. Now mu naught by 2 pi you will have. Now mu naught by 2 pi is nothing but 2 into 10 to the power of minus 7. Okay, so this is the amount of force that you will get if you have 1 ampere current passing through both the wires. So this is how you define ampere, nothing else, a fancy definition. Okay, physicists always want to define the quantities in measurement of forces, etc., so that you can measure it. So this is one of the fancy definition of ampere, and in exam also they will ask you that derive the relation between two parallel current carrying wire and also define ampere. So this definition you have to remember. Now one more thing is that if the current is being carried in the same direction, that is parallel, okay, the forces basically they attract each other. What happens? They attract each other. But if the current is anti-parallel, okay, so in that case the force will be in the opposite direction, they will repel each other. Parallel currents attract, anti-parallel currents repel. Okay, you have to remember this as well for fill in the blanks as well as MCQ questions. Now let's move on to the next part. Torque on a rectangular current loop. So if you consider a rectangular current loop carrying current placed in a magnetic field, now magnetic field here is produced by static magnets, okay, north pole and south pole. So if you are allowing current to pass through a loop, it will also experience a torque. Okay, remember dipole. So dipole kept in an external electric field, so this is a dipole kept in an external magnetic field. It will also experience as a torque, and that expression for torque is given by IAB. Okay, IAB, or you can also write this as IA cross B. Now the magnetic moment of a single loop is defined as M equals to I into A. So this is called magnetic moment. Okay, so magnetic moment similar to that of dipole moment. Here we have magnetic moment. So magnetic moment is I into A. Its unit is ampere meter square, right? Ampere is current, meter square is area. So you have to also remember the unit of magnetic dipole moment, a very important for your objective question. So its unit is ampere meter square. Okay, for n number of turns, if now one important thing about a loop, why loops are important, because loop you can create in one, you can create in multiple times as well, right? So loop can be produced not only once, you can produce loop multiple times. That's why loop is very important, especially in the chapter magnetism. Okay, so if you increase the number of turns by n times, then the same torque can be written as NIA, and the torque can be written as M cross B. Okay, so the magnetic moment will become NIA and the torque will become M cross B, MB sin theta. Okay, scalar wise MB sin theta. Now moving coil galvanometer, the principle of a torque getting applied on a coil, okay, is basically applied in this is an application of the previous theory. Okay, the theory is that if you keep a current carrying loop in a magnetic field, it experiences a torque. Torque means what? Torque means it's try to rotate. Okay, it tries to rotate in the external magnetic field. Now what happens is that you have a system, okay, you have a system where a magnetic field etc everything is set it up, and you want to measure the current. How can you do that? You measure the torque. So you have a loop, okay, through which if current passes, then it will experience a torque. You measure the torque by some mechanism. Okay, if you can measure the torque directly, you can measure the current. Okay, higher the current, higher is the torque, right? You have seen that it is basically magnetic moment into magnetic field, right? So torque was what? Torque was MB sin theta, right? What was M? M was NIA. Now N is in your hand. N is number of turns in the coil. Okay, I you are trying to measure. Area is again fixed. Area is fixed. Okay, magnetic field is fixed. It is basically the magnetic field that you are using over here. So magnetic field is also fixed. Theta is also fixed. Okay, so what happens is that, so the torque basically changes with the current. So torque is directly proportional to the applied current. Torque is directly proportional to the applied current. Okay, so if you apply a spring, if you apply some spring, okay, having a fixed spring constant, that spring will balance the torque. Okay, and you can measure the exact current that is passing through it. Okay, so the deflection, this is called deflection. Deflection means initially this is 0 and it deflected to some angle theta, phi, okay, angle phi, then this phi is basically proportional to the current. Okay, so from this torque to this phi there is a one small step. Okay, I will cover that in my 235 marker section as well. This is a very new question which might come in your midterm exam, so you cannot skip that. The construction and explanation of the working principle of a galvanometer is also a 5 marker possible question. Okay, so here phi is called the angle of deflection, and G equals to NAB divided by K is called the galvanometer constant. Okay, this is called galvanometer constant. Now if you see that NAB is basically coming from this NAB. So how this K is coming, we can come that later on. Okay, Anyway, so this is called galvanometer constant. So if you see whenever you see a galvanometer constant, basically it's this quantity. Okay. Now galvanometers can be converted into ammeter and voltmeter. So first we will see how you can convert it into an ammeter. To convert a galvanometer into an ammeter, we have to connect a small resistance, small value resistance of the wire should be very small, and they are called shunt. Okay, shunt resistance. So an ideal ammeter should have zero resistance. Okay, but zero resistance is not possible. In practical ammeters, the resistance is kept as low as possible. To convert a galvanometer into an ammeter, we need to connect a shunt. Shunt means small value resistance. Okay, a shunt resistance in parallel to the galvanometer, and the current in the galvanometer can be calculated using this formula: Ig equals to I into S by G plus S. Okay, this formula sometimes comes handy. Okay, you can use series and parallel combination concept as well. As you can see, this galvanometer has a current Ig, and the I minus Ig current is passing through the shunt. So the voltage drop across this galvanometer should be equals to voltage drop across this shunt resistance S. So based on that also you can solve the question, numerical question, especially 3-marker numerical question on the conversion of galvanometer to ammeter and voltmeter, of course, are common. Okay. Now in case of galvanometer, what we do, we apply a very high value resistance in series with the galvanometer. Ideal voltmeter should have infinite resistance. Okay, so ideal voltmeter should have a infinite resistance. Now if you are not sure why it is so, you can ask your lab experiment teachers. When you are doing this experiment in lab, you will be using ammeter and voltmeter. So why it is so, why ideal ammeter should have a very low resistance and ideal voltmeter should have very high resistance, for that you can ask the lab instructor when you are performing it in the lab. Okay, I'll leave it blank over here so that you can think upon it. Okay, to convert a galvanometer into a voltmeter, we need to connect a very high value resistance in series with the galvanometer. The voltage sensitivity, sometimes it might be important, is given by phi by V equals to NAB by RK. Now remember that voltage sensitivity cannot be increased by increasing the number of turns in a galvanometer. Okay, you can increase the number of turns to increase the sensitivity of an ammeter, but not of a voltmeter. Okay, this is the last topic of this chapter. I'll be back with the MCQ very soon. Till then, bye.